Saturn is the jewel of the solar system, the sixth planet from the Sun, the second largest after Jupiter, and beyond any argument the most beautiful, for it alone wears a bright and sweeping system of rings that has made it the emblem of the planets since the first astronomers turned their telescopes upon it. It is a gas giant, a vast ball of hydrogen and helium with no solid surface anywhere upon it, 95 times the mass of the Earth, and yet, as we shall see, so lightly built that it would float on water if an ocean could be found to hold it. Almost everything in this chapter has been transformed by a single spacecraft, Cassini, which orbited Saturn for 13 years, from 2004 to 2017, and ended its mission by diving between the planet and its rings, a series of daring final orbits that rewrote our understanding of nearly every feature of the Saturnian system. Much of what follows is the harvest of that mission. Saturn's defining physical oddity is its lightness. Its average density is less than that of water, the only planet of which this is true, so the familiar image of Saturn floating in a giant bathtub is, if impractical, at least dimensionally honest. This extreme low density reflects a body made overwhelmingly of the lightest elements, and being smaller than Jupiter, less compressed at its heart. That same combination makes Saturn the most flattened of all the planets. It spins once in about 10.5 hours, and being fluid and loosely bound, it bulges so far at the equator that its equatorial radius exceeds its polar one by nearly 6,000 kilometers, a squashing you can see at a glance through any telescope. Curiously, its exact rotation period was for decades uncertain, because, unlike every other giant, Saturn gives off no clear rhythmic signal by which to time its spin. The true figure, close to 10 hours and 33 minutes, was recovered only at the very end of the Cassini mission, and by a wholly unexpected means, by listening to the planet's rings. Saturn circles the Sun at nearly 10 times the Earth's distance, taking about 29.5 years to complete a single orbit, so a human lifetime spans only 2 or 3 Saturnian years. At that remove the Sun's warmth is faint, barely 1% of what falls on the Earth. But unlike Jupiter, Saturn is tilted on its axis by nearly 27 degrees, close to the Earth's own tilt, and so it has pronounced seasons, and most beautifully the rings themselves open and close to our view across the long year, tilting from edge-on invisibility to their full glorious breadth and back again. And here, as with Jupiter, lies a deep clue to the planet's inner life. Saturn radiates into space far more heat than it receives from the distant Sun, nearly twice as much, and by some reckonings more. Something within the planet is generating warmth, and in Saturn's case the puzzle is sharper than in Jupiter's, for the smaller, faster-cooling world ought by now to have less heat to give, not more. To the eye, Saturn's atmosphere is a subtler thing than Jupiter's, banded in the same way, with pale zones of rising gas and darker belts of sinking gas running parallel to the equator, but softer, blander, its colours muted beneath a deep golden haze of hydrocarbons that ultraviolet sunlight brews from the methane in its upper air, yet that placid face conceals ferocious motion. The winds of Saturn are among the fastest in the solar system. Its broad equatorial jet blows eastward at 400 to 500 meters every second, well over 1,000 kilometers an hour, far swifter than anything on Jupiter, and its jet streams, like Jupiter's, hold their latitude stable across decades of watching. Beneath the visible haze, the same three-tiered structure of cloud is thought to hang as on Jupiter, a high deck of ammonia ice, a middle deck of an ammonia and sulfur compound, and deepest, a layer of water cloud, each sitting somewhat lower on colder Saturn than on its larger neighbour. By composition, the atmosphere is close to the Sun's, though not identical, about 96 parts hydrogen to a little over 3 parts helium, with a trace of methane, ammonia and other compounds mixed in. That helium figure is itself significant, for it is markedly lower than Jupiter's, and lower than the mixture from which Saturn is thought to have formed. Helium has somehow been drained from Saturn's visible atmosphere, more thoroughly even than from Jupiter's, a shortfall that, as on its neighbour, points not to anything happening at the surface but to a strange process unfolding far below. The clue in the air is the key to the engine within. The missing helium and the mysterious surplus of internal heat are, it turns out, two faces of a single hidden phenomenon, and to understand one is to understand the other. Every so often, Saturn's blandness is shattered. Roughly once in each of its long years, about every 30 Earth years, a colossal storm erupts in its northern hemisphere and spreads until it encircles the entire planet, a brilliant white outburst visible even from Earth, known as a Great White Spot. The most recent, the Great Storm of 2010 and 2011, was studied in detail by Cassini, whose instruments detected for the first time the signature of water ice carried up to the visible cloud tops, hauled there by violent convection rising from the water layer some 200 kilometers below. These periodic eruptions are a revelation, for they show that beneath Saturn's serene and hazy exterior, the deep atmosphere is moist, turbulent, and capable of sudden, globe-spanning fury. The placid face is only a veil over a restless interior. The mystery of the missing helium and the surplus heat is resolved by one elegant idea: helium-rain. Deep inside Saturn, at pressures of 1,000,000 or more times the Earth's atmosphere, hydrogen turns into a liquid metal, and, at those depths in Saturn's particular range of temperatures, helium no longer mixes freely with it. Instead, the helium condenses into fine droplets that, being heavier, rain downward toward the planet's core. That falling drains helium from the outer layers, explaining the atmospheric shortfall, and as the droplets descend, they release gravitational energy as heat, feeding the planet's inner warmth. The beauty of the explanation is that it accounts for Saturn's very puzzle. Because Saturn is colder than Jupiter, the conditions for this helium rain are more widespread, and the rain more vigorous. So the smaller planet, against first intuition, generates proportionally more excess heat than the larger, precisely because it has cooled further into the range where helium separates and falls. Here again the temptation arises to see a great warm ball of hydrogen as a would-be star, and here again it must be resisted. Saturn's heat comes not from nuclear fire, but from the same slow gravitational settling that warms Jupiter, augmented by the helium rain draining through its depths. To ignite even deuterium, the easiest of nuclear fuels, a body must be some 13 times the mass of Jupiter. To burn ordinary hydrogen as a true star does, around 80 times. Saturn is barely a third of Jupiter's mass, far less than 100th of the least of those thresholds. It is unambiguously a planet, kept warm by falling helium and gentle contraction, not by any fusion. In its core, what internal fire it possesses is only the fading warmth of its birth and the slow surrender of its own weight, enough to stir its winds and drive its dynamo, but nothing remotely like a star. To descend into Saturn would be to pass, as into Jupiter, through a single deepening ocean of hydrogen rather than any succession of solid floors. For a great fraction of the way down, the hydrogen is molecular, an insulating fluid churning with convection. But deeper, proportionally deeper than in Jupiter, because Saturn is less massive and its interior less fiercely compressed, the pressure at last grows great, enough to tear the hydrogen into a metal, its electrons set free, the fluid turned into a conductor of electricity. This buried metallic sea, smaller and more deeply sunk than Jupiter's, is the seat of Saturn's magnetism. Deeper still the temperature climbs to many thousands of degrees, in a hot, dense metallic ocean enclosing the planet's heart, whatever at the very center that heart turns out to be. That question, what lies at Saturn's center, was long answered with a confident picture, a compact core of rock and ice, 10 or 20 times the Earth's mass about which the gas had gathered. Cassini's final orbits overturned it, diving 22 times through the narrow gap between the planet and its innermost ring. The spacecraft let itself be pulled by Saturn's gravity with a precision never before achieved, mapping the planet's mass distribution in fine detail. Two things emerged. First, the winds we see at the surface are no mere skin. They reach some 9,000 kilometers down into the planet before the deep metallic hydrogen breaks them. And second, the core is not compact at all, but dilute, a fuzzy, gradual region in which the heavy elements are smeared outward and blended into the metallic hydrogen, spread through perhaps half the planet's radius rather than gathered into a hard central ball. The old clean line between core and envelope, here as at Jupiter, simply dissolves. Saturn keeps one feature that is wholly its own, and one of the strangest sights in the solar system, a gigantic hexagon at its north pole. It is not a marking but a river of wind, a six-sided jet stream, its corners sharp, encircling the pole in a shape of almost geometric precision, some 30,000 kilometers across, wide enough to swallow two Earths side by side, with a hurricane-like vortex spinning at the pole within it. It was first glimpsed by the Voyager spacecraft as they swept past in 1980 and 81, and when Cassini arrived a quarter of a century later, there it still was, essentially unchanged, a coherent six-sided pattern that has held its form for at least 4 decades, outlasting by far anything a storm on Earth could manage. A hexagon drawn in wind, standing for generations. Nature rarely offers a stranger regularity. How can a spinning fluid draw and hold a hexagon? The leading answer is that it is a standing wave. A fast jet stream made unstable by its own shear need not remain a smooth circle. It can buckle into a fixed, wavy pattern locked onto the flow, and for the particular speeds and scales at Saturn's North Pole, the pattern that emerges and sustains itself has 6 sides. This is no mere speculation. In the laboratory, physicists spinning fluid in a rotating tank have produced exactly such polygonal jets, triangles, squares, hexagons, with the number of sides set by the rotation and the shear, and Saturn's conditions fall squarely in the range that yields 6. Tellingly, Saturn's south pole bears no such hexagon, but a simple cyclone instead, proof that the shape belongs to the particular jet at the north, not to poles in general. And Cassini found that the hexagon may be no thin cap of cloud, but a towering column, for a matching 6-sided pattern appeared hundreds of kilometers higher, in the warming air of the polar stratosphere as summer came on. Saturn's magnetic field, generated by that deep metallic dynamo, is about 20 times weaker at the cloud tops than Jupiter's, though its great size still gives it an enormous reach. But its truly remarkable quality is its symmetry. The magnetic axes of most planets, the Earth's, Jupiter's, are tilted at an angle to their spin axes, which is why a rotating planet flashes a regular magnetic signal, like a lighthouse, by which its spin can be timed. Saturn's field is aligned with its rotation axis to within a tiny fraction of a degree, the most perfectly symmetrical planetary field known, so nearly aligned that it offers almost no rhythmic beat at all. This is precisely why the planet's rotation period was so maddeningly hard to measure, and had in the end to be prized out by other means. Yet Cassini's closest passes revealed that the field is not wholly featureless. Fine, banded magnetic structure lurks beneath the smooth symmetry, a genuine puzzle for the theory of how such a field can be generated at all. Around the planet, the field carves out a vast magnetic bubble, the second largest in the solar system after Jupiter's. And as at Jupiter, it is fed from within not chiefly by the solar wind, but by a moon. Tiny Enceladus, jetting water vapor into space from its south pole, supplies the great cloud of electrified gas that fills Saturn's magnetosphere, flung outward into a broad sheet by the planet's rapid spin. Where that circulating plasma can no longer keep pace with the turning field, energy pours down toward the poles and kindles Saturn's shimmering aurorae, which Cassini and the Hubble telescope watched glowing in ultraviolet light. Saturn sits, in this as in much else, between its neighbours. Its aurorae are driven partly by the solar wind, as the Earth's are, and partly from within, as Jupiter's are, an intermediate case that helps illuminate both. The most elegant of all Cassini's discoveries was that Saturn's rings are not merely an ornament, but an instrument, a seismograph for the planet within. The rings are a vast, delicate disk of countless orbiting particles, exquisitely sensitive to the smallest changes in Saturn's gravity. And Saturn, as a great fluid body, quietly vibrates, ringing with slow global oscillations like a struck bell. Each such vibration makes the planet's gravity flicker in a faint, rotating pattern, and where that pattern beats in time with the orbit of the ring particles at a particular radius, it raises a spiral wave in the rings, a ripple frozen into the ice, recording the planet's inner music. Studying waves in the inner rings that no moon could explain, astronomers realized they were reading Saturn's own oscillations, written in its rings. The idea even has its own name, chronoseismology, the seismology of Saturn. That reading paid a double reward. From the exact rhythm of the ring waves, astronomers at last recovered Saturn's true rotation period, the 10 hours and 33 minutes that the symmetric magnetic field had hidden, breaking a deadlock that had stood for decades. And more surprisingly still, the precise pattern of the planet's vibrations proved richer than a simple, fully churning fluid ball should allow. There were extra notes of a kind that can only sound if part of Saturn's deep interior is stably layered rather than freely convecting. A gradual, dilute core of the very sort the gravity measurements had suggested would provide exactly such a stable so the rings and the spacecraft's own path, two utterly different methods, arrived independently at the same remarkable conclusion, that Saturn's heart is smeared and fuzzy, not hard and sharp, reaching out through half the planet. The rings themselves, seen close, are a wonder of structure. They are the largest and brightest in the solar system, sweeping outward more than 60,000 kilometers from near the cloud tops, and yet they are astonishingly thin, in most places only tens of meters from top to bottom, a sheet more slender in proportion than a page of paper. They are made almost entirely of water ice, which is why they gleam so brightly, in particles ranging from grains of dust to boulders the size of houses, each on its own orbit. They exist because they lie too close to the planet ever to gather into a moon. Within a certain distance, Saturn's tides pull harder than the particle's own feeble gravity can bind, so the ice can never coalesce. And the many moons beyond sculpt the rings from afar, their gravity opening gaps and raising waves. The broad Cassini division, that dark lane dividing the two brightest rings, is swept clear by the tug of the moon mimas. For all their grandeur, the rings may be startlingly young and fleeting. When Cassini weighed them in those final plunging orbits, it found them far less massive than expected, only a fraction of the mass of a modest moon. That matters because a very old ring system should by now have been darkened by the slow rain of interplanetary dust over billions of years. Instead, the rings are clean and bright, as if freshly made. Together, these clues suggest the rings are no ancient companion of the planet but a recent creation, perhaps only tens or a few hundreds of millions of years old, young enough that the dinosaurs may have looked up at a Saturn with no rings at all. And they are passing. Cassini watched, ring material raining steadily down into the planet's atmosphere, so that the glory we see may be a brief episode in Saturn's long life, destined to drain away. We may simply be fortunate to be watching during the short age of the rings. Saturn's family of moons, more than 140, the largest retinue of any planet, is crowned by Titan, the second largest moon in the solar system and the only one anywhere wrapped in a thick atmosphere. That atmosphere is denser at the surface than the Earth's, and like ours, made mostly of nitrogen, but shrouded in an orange smog of complex organic molecules brewed from methane by sunlight. Beneath it lies a world eerily Earth-like in form yet utterly alien in substance, for on frigid Titan it is not water but liquid methane and ethane that fall as rain, carve river channels, and pool into great polar seas. Cassini's most audacious act was to loose a European probe named Huygens, which parachuted through Titan's haze in 2005 and landed softly on its surface, the first and still the only landing on a world in the outer solar system, sending back the image of a shore strewn with rounded pebbles of rock-hard ice. Titan, thought to hide a water ocean beneath its crust as well, is now among the most tantalizing destinations in the search for life, and a NASA rotorcraft named Dragonfly is being sent to fly across it. If Titan is the grandest of Saturn's moons, tiny Enceladus is the most astonishing. Barely 500 kilometers across, it should by rights be a frozen, inert little ball. Instead, Cassini found it venting great plumes of water vapor and ice into space from four warm fractures near its south pole, nicknamed the Tiger Stripes. Flying directly through those plumes, the spacecraft tasted their contents and found not just water but salts, grains of silica, and a medley of organic molecules, together with hydrogen and carbon dioxide. The salts and silica betray a global ocean of liquid water beneath the ice, in contact with a rocky floor, and the particular mix of gases is the chemical signature of hydrothermal activity, hot water reacting with rock at the ocean floor, the very kind of setting that nourishes life around the volcanic vents of Earth's own deep seas. In a single small moon, Cassini had found liquid water, warmth, and the raw chemistry of life, all together. Enceladus stands today among the most promising places in the solar system to search for life beyond the Earth. Beyond these two lie the mid-sized icy moons, each with its own character. Cratered Rhe and Dione and Tethys, mimas bearing one crater so huge it gives the little moon the look of a certain fictional battle station, and strange two-faced Iapetus, one hemisphere bright as snow and the other dark as soot, girdled by a curious ridge that lends it the profile of a walnut. Together with the rings and the great moons, they make the Saturnian system a miniature solar system of its own, and one of the richest that any spacecraft has ever explored. When Cassini's fuel ran low in 2017, its makers sent it to burn up in Saturn's atmosphere rather than risk one day contaminating Enceladus or Titan with earthly microbes, a deliberate, respectful end to a mission that had remade our picture of the planet. Much of Saturn is now well understood. Much remains open, the exact reach of its fuzzy core, the true story of its young rings, the deep roots of its hexagon. These are the questions a future return to Saturn will be sent to answer, in the light that Cassini first cast.